linear regulator experiment, and thank you. So let's look at an inverting amplifier circuit made using the LM741 Opamp. So this LM741 Opamp is used in the inverting configuration. Pin 2 is connected to the input signal, pin 6 is connected to the output signal, and then the non-inverting input pin 3 is connected down to ground. There is an input resistor of 1 kilo ohms before the pin number 2 inverting input, and then there is a feedback resistor between pin 2 and pin 6 which is of 10 kilo ohms. So 10 kilo ohms divided by 1 kilo ohms gives us a ratio of 10. So that is the gain of this op-amp circuit. So an op-amp is basically a device which takes multiple inputs at its inverting and non-inverting pins, and then it can amplify it, it can attenuate it, it can compare, and so on. It has many functions which we can utilize it. So in this configuration, as I said, this is in the inverting configuration. So if you look at the output, the output voltage is in pink and the input voltage is in yellow. So the input voltage is 1.02 volts while the output voltage is 9.68 volts. So this gives us almost a gain of 10. It is slightly less than 10, it is more like 9.5, but that is acceptable. The resistors we have chosen, they are 5% resistors. 5% resistor basically means that the resistance can vary by plus 5 and minus 5%. If we have a 1 kilo ohm resistor, the resistance can vary by 50 ohms plus and minus. If we have a 10 kilo ohm resistor, the resistance can vary by 500 ohms. Because the resistance can vary by 500 ohms on the 10 kilo ohm and by 50 ohms on the 1 kilo ohm one, there can be a variation in the gain that we get. Also, there are some resistances in the breadboard and some losses here and there, some inaccuracies here and there. So roughly speaking, the gain we are getting is 10. 9.5, 9.6 is close enough to 10, and that is our result. Another thing to note is the phase. The phase of the input and output is 90 degrees apart. So if we measure the phase directly, we can use the measure function and go to type and then select channel 1 and then select channel 2, and then we can measure phase. So phase is 179.65. So basically 180 degrees apart. 180 degrees apart basically means the input is inverse to the output. That is it for the inverting configuration. Now let's look at the non-inverting configuration. For the non-inverting configuration, the resistors stay in the exact same place, but the input, instead of going to pin number 2, it goes to pin number 3, and we remove the wire which was taking it to ground. So again, let's come back to the circuit. What we will do is we will remove the wire which was taking it down to ground. So pin number 3, instead of connecting it down to ground, now this was the power supply. So instead of connecting pin number 3 down to ground, we are going to take the signal and connect it there. Now we are getting our output. Input and output. Wait. Additionally, we are supposed to connect the resistor to ground. So you can refer to the circuit diagram for the connections. But now the gain formula is 1 plus the feedback resistor by the input resistor. So it is 1 plus 10 by 1. So it is 1 plus 10, so 11. So we should be getting a gain of 11. And if we observe the voltage now, we get 11.12 at the output, and the input is 1.08. So again, this is much closer to the value that we expect, and the phase difference is less than 1. So it is just oscillating between 1 and 0. That is just because of noise. So if we neglect the noise, the phase difference between the two is basically 0. So again, the input voltage is 1.08, output voltage is 11.12. If we calculate it, we will get a gain of 11, roughly speaking. The reason being, in the inverting configuration, the formula changes from RF by R to 1 plus Rf by Rin. That is it for the op-amp circuits measurements, and we can also vary the frequency. So I'll just vary the frequency and show that the output voltage does not change much at all, because the op-amp is pretty stable across the large frequency range. There is something called gain bandwidth product. A gain bandwidth product for an operational amplifier is basically gain multiplied by the bandwidth, which means the higher gain you take from an operational amplifier circuit, the lower the bandwidth will be. So if we keep a gain of 10, the bandwidth will be good. If we keep a gain of 100, the bandwidth will be narrower. If we keep a gain of 1000, the bandwidth will be extremely narrow. So that is one trade-off you have to remember with operational amplifiers. They have a gain bandwidth product, and you have to keep that gain bandwidth product in mind. Other things to keep in mind are the input offset voltage, which can cause issues if you're trying to measure the voltages with a single power supply rail. Then you can look at the input offset current, which will load down your input. In this case, the function generator does not get loaded down much at all. And if we look at the voltage at 22 kilohertz, the voltage is about 10.04. So the voltage has started to drop. If we keep on increasing the frequency, the voltage is starting to drop and it is starting to deform. So at about let's say at 38 kilohertz, we reach the minus 3 dB point, which is at 38 kilohertz, and the minus 3 dB point is 7.7 volts. So 77% of the voltage is the minus 3 dB point, and in this case we have reached the minus 3 dB point at 38 kilohertz. If we go backwards, the minus 3 dB point will be a few hertz, so we can neglect it. So the bandwidth of this amplifier is 38 kilohertz. If we change the gain to a higher value, this bandwidth will drop. If we change the gain to a lower value, this bandwidth will increase. So depending on our application, we may require multiple op-amps in series to achieve a higher gain. So if we have two 10 gain amplifiers, the bandwidth will be good. If we have one 100 gain amplifier, the bandwidth will be poor. So that is one thing to keep in mind when working with op-amp circuits. Another thing to keep in mind about op-amp circuits is that the output drive capability is quite poor. You cannot drive significant loads with this circuit. You can only drive high impedance loads. If you have a low impedance requirement, then you have to go for a BJT buffer or a MOSFET buffer in linear region. That is it for the op-amp circuits, and thank you.